Good afternoon, everyone. Just waiting to see, more attendance here. I hope my voice is clear. Let me open the chat here. So, good afternoon. Thanks. Perfect. So, how's everyone doing? I hope everything is okay. I hope the first week of the problem analysis session was helpful. Any comments? Anything that we can improve in these sessions to make you a little bit more interactive? Do you have any concerns? Waiting to hear from people. No? Perfect. Yeah. So just waiting a couple of minutes here for people to join for the tutorial. Yes. Anything that we can do better? Did you find the recording of the lecture is helpful? Some people have seen less number today, so I'm not sure people can skip this and just listen to the recording. I don't mind of this, but the most important thing is just make sure that you have enough interactions and you get the best out of the course. Could come around a bit more. I don't know. I don't understand this.
Like come into the breakout rooms, I think he means.
Oh, okay. Yeah, it's kind of difficult in the beginning. I hope next time will be much better. The thing is, there's a lots of technical difficulty, try to jump from one room to another room. I hope we already fixed this for this week, so hopefully next time will be better. So I have 2 TAs actually for each tutorial session. That's why I try to, as much as we can, jump to all the rooms. I've seen some comments here. Okay. Doesn't include the lab reports. I think it's if you don't mind, guys, I receive lots of emails and stuff, so it's going to be very hard for me to really respond to everyone. I asked TA to address some issues related to labs and tutorial sessions. Some of the technical questions I would prefer if it's posted on the discussion forum on the course link. So when somebody responded, it's going to be capture all the common questions among all of the people in the section. I encourage also people to have more discussion in these tutorial sessions as well. But forgive us if we can't respond to all the emails. If there are some very important issue of any email, I will definitely try to respond. But any question related to the materials and stuff like that would be better to have some discussion in office hours, in the tutorials, and in the discussion forum. So lab 1 is due at the end of this week, and I mentioned that you have the lab video posted on the course link, so you can watch the lab video. You can ask the TA. It is an impact on the jets. Yes. So you can ask the TA, the lab technician, about any missing information, or I made it very simple because the idea here, in order to help you to how to compile a good technical lab report, because we are missing the hands-on element for this semester. But yeah, so I think this is all what I have for questions here. Some of the thing I noticed in the first tutorial is when you see the solution manual, the solution manual is kind of like jumping into the solution, like, putting the equation and try to put, block number and just get the answer. That's not the idea in this course, and that's not my style of looking into the solution of the students in exams or even in real life. You should really be able to kind of, do some analysis in the problem, just get step-by-step kind of analysis in order to solve these problems, because in many cases, like those formulas or this equation that is posted in the solution manual, it's for this very specific problem. So if you change the geometry, if you change something in the problem, you might end up with a different formulas or something like that. So I would encourage everybody to really go from the principles and put the assumptions and go over, the problem analysis. This is going to be much better, because so far we only had one chapter. So things are not that, huge and difficult, and there's so many, it's very limited number of information that we cover so far. But as we go in the course, and that's, I think this is the most important thing about fluid mechanics. It can be very easy if you understand, very easy if you understand, because it's a very simple principle if you apply it and if you understand it. But it becomes very difficult if you try to, link every single problem to a single like formula and stuff like that. So I encourage people to have general understanding of the topic more than very specific things about every single problem. This way it will be much easier for you to study for the course and pass it without any problem. So let me share this, the screen with you here, so we can start working on our topic for today. Hopefully, no technical problems. I hope you can see this. Let me open the chat here. Okay, so today we're going to talk about fluid statics, and mainly chapter 2 is talking about pressure distribution in fluids. So we'll just, in a couple of seconds here, we'll understand why we are actually covering this part of the material. So in this chapter, we're going to talk about like pressure and pressure gradients, equilibrium of the fluid element, pressure measurements, hydrostatic pressure forces, either on flat surface or curved surface, and pressure distribution in a rigid body motion, and also gonna cover quickly the buoyancy. So when we're talking about statics, and if you remember when we classified the topics of fluid mechanics, we said we're gonna talk about fluid dynamics and fluid statics. So fluid statics here is referring to forces on the fluids, and this fluid is stagnant or at rest, right? So we are not considering motion in these fluids in this chapter. And in this case, we are not considering any shear forces applied on this fluid as well. So we are concerned with normal forces, which is basically a pressure forces here. And we're gonna cover, forces coming from a stagnant fluid at equilibrium in this chapter. So yeah, the slide is posted, you should have it. So yeah, I'm gonna maybe focus more on the lecture here, because it's very hard to capture what's happening in the chat here. So anyway, so this is a fundamental of the hydraulics and the storage and transport of fluids, and we'll understand why we are studying this material here. If we're looking at this slide here, we are concerned with application like, for example, building dams for hydrostatic power generation. So when I talk about static forces here, I'm considering basically, the design of this kind of, dam and stuff like that. So I'm not really looking into the turbine part here. So my concern in the fluid statics is how to make these, how to design these gates, for example, how to design this, structure in order to hold a fluid that is mainly like a huge tank. So we can assume that this fluid here inside this tank here is a stagnant fluid or static fluid. Everyone knows, like, you know, when we go for diving, at every point underwater here, as you go down, the pressure is increasing, and we have some dial in order to monitor this pressure, and this pressure is affected by the level where the person is underwater. So static pressure is basically what we are considering when we are underwater as well, for diving problems. Many applications for the fluid component or machinery or equipment, right? For example, submarines. When we are designing submarines, we are considering, for example, you know, forces over the surface, right? So we are kind of, you know, looking into what will be the pressure forces over the surface in order to design these submarine materials and so on. Also, we can consider the motion of the submarine by having more liquid coming inside the body of the submarine, which is increasing the weight of the submarine. So the submarine can go up and down based on the balance of the forces and based on the buoyancy force as well, that what we will discuss for this chapter. Fluid transportation, like, you know, oil transportation, when you have, like, you know, a barge here that is offshore and is carrying, like, you know, oil or gas under the sea, the design of this piping, right, will have to have some kind of, you know, some knowledge about what pressure forces coming from outside of the piping, right? Although, like, you know, the fluid inside these piping is carrying gas or natural gas or maybe an oil, and it has a pressure and so on. We are not considering the fluid inside, but we are considering the pressure forces that is coming from outside, based on, you know, the depths or the location of those piping under the sea. Other application very important to cover in this chapter is also related to fluid transportation. So fluid transportation here, I'm not talking about pipeline. I'm talking about, like, you know, trucks that is carrying, you know, tanks, and these tanks are basically filled with liquids or maybe compressed gas. So it's basically, it has fluids, and this fluid is moving in this direction, you know, with a truck, but inside the fluid is actually doesn't have any shear forces. So now we are talking about bulk, you know, transportation of fluids. So the whole fluids, all the particle of the fluids inside is considered to be a static fluid, but now with a linear kind of acceleration. So we're going to cover this in this chapter. In addition to fluid storage, like, for example, most of the oil and gas, you know, pipeline is carrying pipeline from one country to another country, and when it's you know, exported, it's stored in tanks like this. And for people going to be working on the oil and gas industry, they will find that the design of these tanks is, you know, it's a very kind of a detailed kind of analysis when you are looking into different level of oil inside these tanks. So all these kind of application will involve some understanding of statics forces coming from the fluid, how can we design these tanks, and so on. So pressure, we all know what does pressure mean, right? So pressure in general is, anyone?
Force over area.
Force over area, right? So basically, we're talking about, like, you know, in general, pressure will be force over area, right? And in this case, if we are considering, for example, a pressure of a fluid at a point, we can take an element, and this element can be very small, and then we can define the pressure as the limit of the dF over dA, and dF here is our force, and dA here is a differential element delta A, and if delta A is approaching zero or limits to zero, we are basically considering this, you know, pressure at an element or at a point in a fluid. So in general, it is F over A or dF over dA. So F here is a normal force. One of the things I want you to always consider and keep in mind that pressure force is a normal force, right? So fluid will affect, you know, or generate a, you know, or apply a certain pressure force on the surface, And these forces all the time is normal to the surface. So when we are talking about force here and area here, this area and this force here is normal to the area, right? So that's why when we are talking about pressure, we call it like, a normal stress, right? And pressure is considered to be like, in the fluid as a scalar quantity. And we'll understand what does a scalar quantity mean here, because it has a value, it has a magnitude, right? And equally in all directions, right? Some of the stuff written in this textbook, it will explain this a little bit to you. But as I decided to give you some kind of, a derivation of like, how can we assume that the pressure at any point in a fluid? So if I have a fluid like this and a point here, I can say the pressure in all direction at these points is the same, which means that fluid is not, the pressure of the fluid at any point here, this pressure here at this point is not affected by the direction. All the direction of these pressure forces are of an equal quantity, right? So how can we do this? I will, if you can bear with me here on this analysis, we are selecting a differential element, and this differential element, let's say this is X, and this is Y, and this is Z, right? I selected this element of delta L, okay, at any angle alpha, okay? And why I'm doing this? Because I want to prove that at any angle, the pressure forces here will be equal. And remember, when I selected delta or a differential element, we are talking about a small little element. So this delta here can be approach zero, or the element here can become like 1 point. So this shape here is selected to be like, this area here is at any angle alpha. And the pressure force on this case here would be normal to this surface. So we can call it like Bn. And Bn here is at any angle. In order to find out these forces, so force will be basically the pressure times the area. So what will be the area for this case? The area for this case will be this element here, which is delta Y, and the area here will be delta L. So if I basically, took some balance forces here, so I have to take the forces in the normal direction, and the area here will be delta Y and delta L. So now, if you imagine the three-dimensional shape of this element here, let's assume we have B in the Z direction. We call it BZ. Let's assume also B on this is X direction. So in this direction, right, BX, right? So in the X direction. And all the time, the force is going to the surface. You see here, pressure force is going to the surface. So Z, this is the direction of force. This is the direction of force, right? Now let's look at, we mentioned that we have static fluids. Static fluid mean here, second law of Newton here is basically no acceleration. That means the submersion force would be equal 0, right? So for this element here, let's take the force in the X direction. What will be the force in the X direction? This normal force here is inclined from the surface. And if this is alpha, that this also alpha, which means that the force in this direction will be the cosine, and in this direction will be the sine value, right? So now the pressure in the normal direction times delta A, and delta A is, if you remember, delta Y, delta L, and then will be the sine value because this is in the X direction, right? Minus this force here. So this force here is Bx times the area, right? So, and the area here can be, expressed in terms of delta L, right? So if I have, this is delta L, and this is delta Z, and this is delta X, and this is alpha, right? I can say basically, you know, the pressure in this direction would be this delta Z, but delta Z is delta L sine alpha, right? So in this case will be delta Z times the thickness of this, which is delta Y. So you will see here delta Y, delta L sine alpha, and then multiply by dx. If I look at this problem here and you know, divide by delta L, delta Y, delta L sine alpha, you will end up with Bn is equal to Bn minus Bx equals 0, which is basically Bn is equal to Bx. Why I'm doing this? Because now I am proving that the normal pressure at this point here will be the same value of the pressure in the X direction, right? So which means that now the normal force is equal to Bx over here. I can do the same thing in the Y direction. So in this case will be, you know, this element here, and this is a cosine, and it will be going down, right? So Bn delta A cosine alpha, right? And the pressure force in this direction, we call it what? This is a Z direction, so it should be Bz times delta A. What is the delta A here in this case? It will be all this area. So this is the area I'm talking about here. And this area has this length and this width. This width is delta Y, we know that. And this delta X here can be expressed by delta L cosine alpha, right? So I'm doing very simple, you know, force balance here. Now in the Y direction, what in addition to these forces, what do we have here? We have the pressure force acting on this surface. We have this normal force components in this direction. What other vertical forces we have to consider when we are doing this balance here? Anyone? I hope you are following what I'm saying. What other forces in the, exactly, gravity, right? The weight, right? So you see the weight here now is basically acting downwards. What will be the weight in this case, right? You remember this gamma of the weights is weight divided by volume, right? So I can say that basically the weight is gamma times the volume. What will be the volume in this case? The volume is very easy here to find out because we have a you know, triangle here, right? That has half, right? So this is like, you know, half of the delta L cosine alpha, right? Times the vertical is delta Z, right? And multiply by the width, which is delta L, delta Y, sorry. This will give you the volume. We know delta Z is delta L sine alpha. We know the cosine alpha as well, right? So we have delta L cosine alpha, delta L sine alpha. And this is basically what we have for, sorry, delta X as well, right? So this is, right, delta L cosine alpha. So in this case, we have in the Z direction, we have the normal force component of the cosine. We have this Bz delta Y delta L cosine alpha, and we have you know, the weight. So if we take this as a positive direction, the weight will be in the negative side, and this will be basically the specific weight times the volume. If I divide this whole equation by delta Y delta L cosine alpha, so this term here will be gone, delta L delta Y and cosine, right? I will end up with Bn minus Bn plus delta Z plus still delta delta L, right? And delta, you know, delta L, another delta L here. So, or like if I divided this whole thing. So I will miss this, this, and we'll have only the sine alpha and delta L. And sine alpha, if you remember, is delta Z over delta L, right? So this part here is very small. So we know that if you have a two delta are multiplied together, that means basically if delta is very small, that means delta square will be even smaller. So the Z direction, or the force balance in the Z direction, will end up with Bn is equal to Bz. What does it mean here? First, we have Bn is equal Bx. The second equation is Bn is equal Z. And n here is arbitrary number, right? So we selected this plane at any angle alpha, right? So at any n direction, Bx is equal to Bn, which means that Bn is equal Bz equal Bx, which means that basically I can say that at any element, and remember, when we are selecting an element of delta, that means we are selecting a very small little particle here, right? So this delta can be approaching to zero, that become, this whole shape become a point, right? And when I say that now at any normal direction, at any n direction, the pressure is equal to Bx is equal to Bz is equal, right? So in this case, I can say that basically the pressure is not changing with the angle. So in this case, I can say that, let me add here. So imagine now I put this triangle now very small here, right? So this is Bn, this is Bx, Bz. So you can imagine now, if I make this small triangle is very small, become almost a point, I can say that the pressure at any angle will be the same as Bx or equal to Z. That means at any angle here, the pressure at any point is the same, right? And this is how we can drive the relation for the pressure of the static pressure at any point of a static fluid in any direction will be the same. So at static fluid, right? So in all directions. Okay. Why this is important, you will understand and appreciate, like, as in few seconds here when we start talking about forces on the surfaces and so on, right? Not sure what would change. Yeah, fluid dynamics is different, right? So you remember all these relations that we cover so far is assuming submission of forces equal zero, right? Which means that this whole fluid is stagnant, right? So in this case, the force is balanced altogether. So in this case, I can say that at any point, the pressure is the same. B would into the page, yes, By, yeah. This, if you talk about 3 dimension, also in the y dimension, in the y direction, also will be the same value, right? Good. So pressure, we know that it's the unit for the pressure is force over area. That means basically the dimension will be the same thing. The dimension of the force divided by the dimension of the length. And you guys are expert in this now. So it's Newton per meter square if we're talking about SI unit. Another name for this is Pascal. Newton per meter square is called Pascal. So when we're talking about kilopascal, that means it's 1,000 Pascal, but it's still in SI unit. Okay. One of the very common, units that we use, it's the same SI unit, but one of the very common name, you will see it in the market, or like, in some of the, pressure gauges available in for measuring pressure, is something called bar. And the bar here is about 100,000 kilopascal, or like 10 to the power 5 of Pascal, right? So either 100 kilopascal or 1 to the power 5 of 10 to the power 5 of Pascal. Atmospheric pressure is 101.325 Pascal. Is that same everywhere? Anyone? Atmospheric pressure? No, right? Depend on? Anyone? Exactly, right? It is the same thing, right? From the troposphere to the ground, there's a huge space, right? And this space is filled with air, and in this air, it has a certain weight. So it depends on the elevation. And that's why when we are actually taking off with an aeroplane and goes 30,000 feet above, the pressure is changing, right? So which means that basically atmospheric pressure is changing. So atmospheric pressure here is within the atmosphere, right? But location, the location where you are doing this measurement, or the location where you are actually applying sea level, that's correct, right? So the atmospheric pressure here is a standard value that is equal this value here at the sea level, which is a sea level over the whole, Earth will be the same. So basically, this is a kind of a standard atmospheric pressure. British unit for pressure will be pound force per inch square, and sometimes we call it BSI, pound per square inch. And this is very common in practical application. You will see this is BSI value here given for the pressure. Okay, and it is about 14.7 BSI is equal to 1 atmosphere if we need to convert between one and the other. Good. Other important topic before we get into some problems here, the pressure scale. So everyone maybe heard about gauge and absolute vacuum pressures, right? And all these scales it's just a different reference when you are actually measuring your pressure, okay? And this scale here is, if I look at the pressure here, so at, let's say, 101.3 kilopascal here, right? Let's say, imagine at a certain altitude, the atmospheric pressure is this value here, right? This could be a little bit above, could be a little bit below, based on the attitude of the atmospheric pressure. But any pressure higher than this value, or any pressure lower than this value, can be measured, with a two reference. One reference is 0, right? Because once we are saying that this is 101.3 kilopascal, that means what? It's a number, and this number is a positive number. That means it has a 0, right? And the 0 here is, we call it the 0 absolute pressure. Anyone knows, what is the 0 absolute pressure mean here? Any memory from the physics? How can we reach to 0 absolute of pressure? Space. Yeah, I would add to what people are saying, vacuum. It's a complete vacuum, okay? Because I want everyone here in this class to understand that the pressure forces is coming from those particles of the fluids. So if you have a container, and this container is basically filled with molecules of fluid, this fluid has forces, and these forces is affecting the surface of this container somehow by hitting the wall. So the complete vacuum means no particles, right? So we are removing all the particle in this from this container. So the only way to get into the 0 absolute pressure is with doing a complete vacuum, okay? Or as people mentioned here in the space doesn't have any air, doesn't have any gases. So in this case, we are talking about 0 atmospheric pressure. So is it easy to really get into this 0 absolute in engineering application? Anyone? No, because of the amount of energy required in order to make this complete vacuum, right? So when we are talking about absolute pressure here, and you will see in the thermodynamics, we are always using physical property in the thermodynamic based on an absolute term, So you will hear this a lot in the thermodynamic course. But in fluid mechanics, when we are saying atmospheric pressure is equal 0, what does it mean? Is it absolute? Of course not, because basically, if we are measuring from the atmosphere, right? So if I'm measuring, if I'm taking this is my scale, that means this is my 0 now, right? And I'm measuring from this value, atmospheric pressure here will be, right? So that's why we have something called gauge and absolute scale. Okay. Gauge is referring to the reference of the atmosphere. Absolute mean is referring to the 0 absolute. Okay. Now, if I have a point, like for example, A here, what is the value in absolute? This whole value here, right? And what is the value of this pressure for the atmosphere? It's only this value here, right? So if let's say, for example, let's assume this is 100 for, just easy, right? If this is 100 kilopascal, the atmospheric is 100 kilopascal. If I have a pressure that is equal to 200 kilopascal absolute, what does it mean? What is the gauge value for this? Silence. What happened? No one is. Imagine I have an atmospheric pressure. Yeah. Thank you so much for calculating this. Yeah, this is based on the 101.3, right? So 200 minus the atmospheric pressure will give you the gauge value. So this is basically the gauge value. And if I measure it from the atmosphere, right? So now there is some numbers or some time when we have a pressure that is lower than atmosphere, right? So imagine now if I have 50 kilopascal absolute, what does it mean? 50 kilopascal absolute, what does it mean in gauge? It is lower than the 101.3, right? Which means that it is under the pressure, the atmospheric pressure. And that's why we call it vacuum pressure, okay? So sometimes we say that anyone can calculate this 50 psi, 50 kilopascal absolute. The value will be 51.3, exactly. So if I say 51.3 here mean what? Negative, right? So negative value. So I have to add the negative value in this case, right? Or I can say 51.3 vacuum. So the negative sign can be replaced by the word vacuum. But you should know that when I say this vacuum, 51.3 vacuum mean it is below the atmosphere, right? So I hope this shouldn't confuse anybody. This is just a scale where we are measuring. So we're measuring either from a 0 absolute, or we are measuring above or below the atmospheric pressure. Most of the engineering application is dealing with gauges because we are actually, have our equipment, machines and stuff in the atmospheric, right? So we are always referring to gauge pressure, right? But of course, if we have a physics lab and we are actually doing some experiment in thermodynamics and stuff like that, we will definitely consider some value for atmosphere and so on. Okay, I hope this is clear. Now, I just selected myself to go through this kind of derivation in this chapter here because it's very important to make you, understand that some of the stuff that we are doing here has some basis, right? So we did the analysis when we are talking about like a fluid at a point. So the pressure at every direction at any point in the fluids is equal in all directions. And we did this by assuming some kind of, a triangular element at any angle. We found this, right? There's another very important relation in the fluid statics, which is talking about the pressure gradient. And when I talk about pressure gradient here, we are talking about variations of this pressure, right? Where we'd like to get this variation, we'd like to get the variation in the horizontal plane and in the vertical plane, right? And if we have the variation in the horizontal and the vertical plane, we can get the variation in any other plane, right? So we need to know what is the pressure at fluid, static fluids in a horizontal plane. What is the value? Is there any changes in this value? And what will be the changes in the vertical direction if we are looking into different depths of the fluid and so on, right? So again, in order to prove this theory or try to find out this relation, I'm going to select, a cylindrical element like this. It has a length of delta L, right? And it has an angle alpha, right? And of course, it has a weight, this element. And every time I'm talking about element here, I'm talking about a very small little element, right? So the weight here will be gamma times the volume. And if this element has an area is equal to delta A, that means, the volume will be this area times the length of this element, which is delta L, right? So the volume delta A, delta L times gamma will give you the weight, and it's acting in the in this direction here, so the gravity direction. Now, in order to find out the forces or the force balance here, gamma is a specific weight, right? So gamma is a specific weight, which is weight over volume. The summation force here will be 0 because we are talking about static fluids, stagnant fluids, no motion, right? And if I, if I look at the pressure forces in this direction, I can just say that in this direction here, L, okay, the pressure forces, the pressure will be B times delta A. So the force will be basically the pressure times delta A. What I'm saying here is after a certain delta L, what will be the value of the pressure here? Well, because I need to find out what pressure changes, right? So I'm going to say that the pressure will change from this point by this point after a distance delta L by pressure plus delta B. I can say that, for example, some parameter change from an original position by a value of delta B. So, the variation here will be basically delta B. So the pressure is equal B. Now the pressure has become B plus delta B. This delta B could be more or could be less. We'll find out. But the thing here is like we're trying to relate the pressure variation here along the distance delta L. So I'm going to do the same thing for force balances here. So this is a force in this direction, the force in this direction, right? So if this is alpha, right? So I can say that the weight now is delta L. So I can, this is alpha. This is alpha as well. So in this direction, it will be cosine, and in this direction will be sine, okay? So it will be this value here, right? So in this direction, right? And in the normal direction, it will be cosine, right? So now if I'm taking this as a positive direction of delta L, the pressure here minus this value here in this direction, right? Can, this is just a quick question. Can this force be in this direction, can be in this direction? Yes or no? Can this pressure force be in this direction? Or it has to be coming inside? Some people say yes. No, not some cases. No. No. Why? Just go 1 minute in this presentation. The pressure is a normal force always acting into the area, right? This is what the pressure definition means, right? So if I'm selected, this is the area I'm talking about. So let me just use. pressure forces always acting inside, right, into the area, right? This is what the definition of the force here. So if we're talking about pressure, and this is the element I'm considering, so this is the element I'm considering, right? If I'm looking into the pressure force will be acting all the time into the area, right? And this is what the definition of the pressure is, right? So if I'm taking the summation of force in this direction, L, so PA, B delta A, which is this one here, minus this, right? Minus the component of the weights is equal 0. And I know that basically, you know, so I can just say that now this is minus B delta A minus delta B delta A, and I can divide by delta A, right? So in this case, I can just say that this is delta B now. You see this number here will be gone by minus B delta A. It will be basically delta B. If I divide the whole equation by delta A over delta L, it will be basically delta B over delta L will be minus gamma sine alpha. Okay. So in this case, I have the change of B over delta L and Y delta L here in the direction of, you know, general direction, right? Remember, we try to find out variation in any direction, right? So variation in the L direction, the pressure variation with respect to this delta L is equal to minus gamma sine alpha, okay? And of course, sine alpha is delta Z, and this is delta L, and this is alpha. So sine alpha will be delta Z over delta L. So I can replace sine alpha here by delta Z over delta L. So dB over delta B over delta L equal to minus gamma, and then we have sine alpha, which is dz over dl, right? So I can change this d delta to any change. So dB over dl is equal minus gamma dz over dl, right? I can change now this to delta B over delta Z is equal to minus gamma. And this is the equation I'm trying to find out so far, okay? That means what? The variation of the pressure with respect to Z, remember this is Z, is equal to minus gamma, okay? And what does it mean? The pressure will vary in the vertical direction by minus specific weights. That means I go up, the pressure will reduce or decrease if this is our positive direction here. Increase or decrease? dB over dz is equal to minus gamma. Yeah, because there is negative here, right? The more I go in the z direction, like I go up, that means increasing of delta z, the pressure will decrease. The more I go down, it's basically increased because, right? And why this is happening? Zero. I don't know what does zero mean here. Okay, so if I go up, that means I'm increasing the distance in the vertical direction, right? And remember, like, you know, delta Z is actually the direction of gravity, right? This is, we're talking about fluid here, right? And this term here that we are talking about here is, or this weight here, this is where the gamma come from, right? So gamma come from the component of the weight in the vertical direction, which is the Z direction, right? So in all cases, when we have dB by dz is equal minus gamma, so I can say that this dB is equal minus gamma dz. Everybody agree on this? Okay. I can take the integration if I want between 1.1 and 0.2. right? Between any 2 points, right? What do you think if this dz is not changing? dz is not changing, mean what? I go from one point to another point, has the same z. What does it mean? Same pressure, yes. Yeah. B is the same because, right? So if let's say, for example, here, this is a fluid. I go from these points to this point here. This is what? This is horizontal, right? So when I have no change, dz here is equal to 0, the pressure dB is equal to, if this is 0, that means what? dB is 0, or B2 is equal to B1, right? And this is the most important first statement in this chapter, is pressure is not changing in the horizontal direction in a static fluid. This fluid has to be static. This is all driven for static fluids. So if I'm going from one point to another point in the same horizontal direction, it's basically like, you know, pressure is the same, right? So B1 and B2 are the same. Now, if I go in the vertical direction, what do you think? You just mentioned this in a few seconds, right? If I go up and down, its pressure will increase or decrease, right? So if I go down, the pressure will increase, right? So in this case, if I have, this is a fluid, and this is point 1, and I go in this vertical direction here, 2. So this is Z1. It's from any like, you know, right? So Z1 and Z2. B2 is greater than B1, right? And what is the difference between 1 and 2? dB is equal to minus gamma dz. If I integrate from 1 to 2, 1 to 2, right? Z1, right? Let me just do this nicer. Right? So which means that the pressure will increase. And that makes sense. Why? Because imagine yourself as a particle actually inside this fluid, right? What do you think as you go down here? Are you carrying more? Right? You are carrying more weight, right? Over your area, right? So as you go down more, you are carrying more weight of the fluid, right? Which means that the weight of the fluid will increase the pressure as you go down. And that's why we're talking about gamma here. And imagine, again, we're talking about a point. So we're talking about a small little area, very little area. So in order to understand the pressure at a point mean, right? So in this case, we are talking about a variation of pressure is equal to gamma H or gamma delta Z, right? Or gamma, you know, was a different, the new Z as you go down will be basically a higher pressure, okay? And remember, this is static fluid, okay? How about for gases? I can apply the same thing for gases, right? Except for gases, I have additional relation. If you remember in the beginning of the course, I talk about something called ideal gas equation, right? So the ideal gas equation, remember, BV equal mRT, and this is volume, and this is mass, or B is equal to M over V, so it's rho RT. This is our ideal gas equation. So, or rho is equal to B over RT, right? And remember, if I multiply this rho by G, it will be basically specific weight. So if I multiply this whole equation by G, it will be basically gamma equal to BG over RT. Okay. Same thing, for, I can, as this is a fluid, so I can apply the same fluid, principles to it, right? So in this case, I have gamma here. So the pressure variation in the Z will be, dB by dZ is equal to minus gamma, right? And I can just replace this by, B over G over RT, right? So gamma is B G over RT. So I can actually get relation between dV over dZ as a function of the pressure as well, right? That's not the point I'm trying to make here, but you can apply variation of the pressure in terms of vertical direction or horizontal direction for gas or liquid will be the same. Maybe you have additional information in the gas because there are some relation between density or a specific weight and the pressure. But in general, what do you think about for gases? If you go, for example, from the 5th floor to the 1st floor, do you think there's going to be some variation of the pressure, at the top of the building and the bottom of the building? You will notice some variation in the pressure. Not too much, right? Slightly. I can take this. Small number, right? Why? Because gamma, right? Gamma is rho G, right? It's the rho or the density. So the more dense fluids, the more variation of the pressure, right? So in this case, if I have, if I'm talking about air or atmosphere, like, or like air in the atmosphere, the pressure is always, some number or like, a fixed number. But if I go a little bit up, 1 meter, 2 meters, 3 meter, 100 meter, 1,000 meter, a kilometer, right? Now I start getting what? I start getting some variation, right? Why? Because the distance is huge now. So delta Z multiplied by gamma, and the gamma now is, small number, but delta Z now is is becoming a big number. And that's why you will see this figure here is talking about, like, the variation of the atmospheric condition at different kilometer up, right? So you'll see here, like, variation here is, changing slightly, and then as you go up, the pressure will decrease or increase. Flying by the aeroplane, the pressure is reduced, right? So basically, increase. Why? No, right? So if you go up, pressure decrease, right? So you will see the variation as you go up, the pressure is decreased. But for gases, you really need to have huge elevation, huge variation in the delta Z, right? Which means that I can do some assumption in many engineering applications. If I'm talking about a room, like, let's consider the room I'm sitting in here. If I'm measuring the pressure at the floor and I'm measuring the pressure at the ceiling, this is about, like, 6 feet or, like, I don't know, 9 feet, right? Do you think there is a big variation in the pressure between the floor and the top of the ceiling? No, right? Because if you calculate the density of the gas or the density of the air is about 1.2, right? Multiplied by G, which is 9.81 times, like, about 9 feet. So it's about like 3 meters, right? The variation is like point something kilopascal, 0.01, 0.1 kilopascal, very small number, right? But if I'm talking about huge distance, I should consider, like, some variation in this pressure. What does it mean? It means, like, in this course, you will find a lots of problem at the end of this chapter is talking about manometers, talking about gas in a tank, gas trapped in a small little pipe and stuff like that. Can you assume in this case the pressure inside this whole container to be the same or not? Thank you. Minecraft. Yeah, thank you. I'm not sure. Not 6 feet, 9 feet. Okay. So now, what is can I assume the gases is has the same pressure inside this container? If I have a container, if I have a small little apparatus, and the gas is trapped in a certain space, can I assume the gas's pressure is the same everywhere? Yes. Okay. Remember this because this will solve a lot of the problem that we have for this shuttle. Okay. And it's coming because of the the understanding of the pressure variation in the z direction. So let's do this exercise now. If I have this fluid here, and this very funny shaped tank, and it has many points here. BA, it's not a capital. Let's see. What do you think about BA in terms of variation from point A to point B to point C to point D?
There's no pressure variation.
Right. So BA is equal to BB is equal to BC is equal to BD. One of the very important thing you have to remember, right, when you are doing this is the same fluids, right? So whatever at the top above A and B and C are the same, right? So one trick we have to keep in mind every time we are looking at these kind of shapes is between A and B, the fluid is static. So everywhere here is the same fluid, right? This is the same fluid, right? So if you go from A to B, you are going in the same fluids. The fluid is connected, right? There's no isolation between point A and point B. This fluid is basically the same fluid, and they are in the same horizontal plane, right? So I can say that this is basically what is BA and BB and C is 0. How about BA and B capital?
They're going to be equal as well.
Right. I don't see, yeah, also the same, right? So basically we have BA and BB will be the same. How about C?
The same as well.
BC as well, right? So in this case, can I say BD also the same or not?
Those can be greater because mercury is denser than water.
Yeah, but I cannot really say that this is equal to BC or BD, right? Why? Because this is fluids. There's a fluid here that is different from this fluid here, right? C and D are not sharing the same fluid static. And of course here, because this is mercury, right? We are expecting the pressure at BD will be more because we are carrying more heavier fluid than BC, right? One of the questions I will ask you, maybe just a simple exercise here. If I have a container like this, and I have water, oil, specific gravity is 0.9. I have mercury, right? And I have let's assume this is a tank. Okay, and I have air. Okay, and mercury is specific gravity is 13.6. And I put all these inside this tank. How do you think the distribution of these fluids inside this tank will be? Let's start with, who's going to be at the bottom part? Mercury. Right? So, next. Water and exactly, right? So next will be water. Right? And then oil. because it's lighter, and then the gas will be, or the air will be at the top, right? Which means that basically we expect every time we have fluids in contact in a static kind of condition, right? The fluid will be distributed based on specific gravity, or like, and this is some maybe an introduction to the buoyancy forces that we're going to cover in maybe next week, right? So, but you have to keep in mind that specific gravity and orientation of the fluid in a container will be basically following the specific weight, or like which heavier fluid than the other. So if you mix all this and then you leave it, it will basically, like, of course, if there is no chemical reaction between those fluids, oil and gas and mercury are not going to be like, any chemical reaction here. That means they're going to separate in, in a different level of this tank based on their specific gravity. Okay. One of the very simple application about this, we learned about, like, pressure variation in the horizontal direction, and we're going to learn about, like, one of the very important applications to this is something called hydraulic transmission or pressure transmission. Okay. And when I talk about pressure transmission here, I'm talking about, like, something like you have seen when you are going to like gas station, or like, car service. He put it on a hydraulic jack here, and then he maybe applies some pressure, and then, this pressure is kind of, lifting a piston, that this piston is carrying the car, right? So there's something called Pascal law in this case that is using the condition for static pressure, and, same value for this pressure from one point to another point. So you can apply a certain pressure of air here for this fluid, and this fluid is acting on a piston, and this piston is moved up by the action of the pressure force. In order to understand Pascal law, or the hydraulic transmission in the fluids, let's consider this example here. So we have a hydraulic jack, and in this case is not operated by pressure or pump or anything. It's operated by hand, and the force applied here is F, and filled with an oil, and this oil has specific, specific weight here as 56 pound force per feet cube. Okay, gamma is given. Neglecting the weight of the two pistons. So I have a piston here, you can see this. And this piston here is this. Okay, so these two pistons here, the weight is neglected of these two pistons. What force F on the handle is required to support 2,000 pound force weight for this design? Okay, so I need to find out this force here. So required is F here. Okay, how can I start this problem now? Looks like these forces applied here, right? What do you think this piston here will try to push in this direction, right? So in this case, how can I start this problem? What is transmitting the forces between this one here and this, this piston here? Torque. Torque is always, when we are talking about rotating element, never say anything about torque when you have, linear motion or something like that. Okay, because this piston is going up and down. This is not a machine rotating. Okay, how do you think I should start approaching this problem? Let's put the assumption first, right? Okay, not assumption here. What is the most important assumption we have to make here? The most important assumption to have to make here is static fluids. Although in reality, I'm gonna be moving this F, so the piston will go down and stuff like that. But let's assume that now just pushing, right, without moving this piston, right? So fluid is static here in this case. And if I say fluid is static here, right, this is the most important kind of assumption, right? And this is the same fluid. Can I say that this point 1 here and point 2 here, this is in the same fluid, are connected, same, like, same fluid between 2 and 1. Can I say that this B1 is equal to B2? Right? This is what we spend all the lecture today, right? So fluid will be kind of, constant between these 2 points here, right? So that's not really an assumption, but this is something based on the static fluid. I can basically say that this B1 is equal to B2. So now I need to find out the pressure here at 1 and pressure at 2. But in order to start the problem, I have to find out what is the relation between this force here that is required and the pressure at this point 1. So I can say that instead of, like, people are talking about torque, I'm talking about moment in this case, right? So if I know that basically this force is applied F here, I can say that this force here is F small, let's say, right? And this force is acting at this point here, right? So I can say that summation of moment around point O is equal 0 for static jack, right? So in this case, I can say that there is no moment forces. And why I'm doing this? Because I need to find out relation between F capital and F small. So I can say that this moment here is 0, right? If I do this, I can say that this basically, F capital times the distance between F and this point, which is about 1 plus this 15. So it's about 16 inches, right? And it's going in this direction. Let's assume this is our positive direction. Okay. Now, in order to say that this force is applied here, I have to basically cut this, this element here. So I have two forces here. One force is applied in this direction, and one force is applied in the other direction in order to have a balance here, right? This is what you learn in your mechanics. So in this case, I can say that this moment coming from this F here is minus F times 1 inch equal to 0. And this F in this direction will be translated if I have it on this piston here. So in this case, I can say that F is equal to F small divided by 16. And this is equation 1. Okay. Now, the second part will be basically for the static fluids, right? Pressure at point 1 and at point 2 are the same. B1 is equal to B2 for a static fluid. And B1 here can be represented by this F over the area of the small piston, right? And B2 here can be represented by this 2000, right? Divided by the area of this big piston, right? And in this problem, the diameter here is given for this piston, and the diameter here is given for this 3 inches, and this is 1 inch, right? So I can say that basically is F over the area, and this is 1 square equal to 2000 divided by the area here is square. I'm trying to be consistent in the units as well here. I didn't convert anything to feet because I didn't need actually to use any, like, the specific weight of the fluid or anything, right? So this is inches square, this is inches square, this is bound force. If I get this F here, it will be in bound force. I can just calculate this as 2 to 2.2 bound force. Okay, and if I get this, so from 2 into equation 1, I can get this F as, this will be F over 16, and it will be about 13.88 bound force. And this is a very typical example of Pascal law. It's basically transporting transmitting forces between one point and another point using the the statics information that we cover for this lecture. Is trying to find out what will be the forces at one point over the other one. So if you have a piston that is big like this, so you can actually use much smaller forces. So you are carrying, trying to lift 2,000, you only need about 13.8 bound force by using this kind of element here. But in reality, you only need at least, if you want to apply it on the piston, you only need 222 at this piston here. So you can play a little bit with some mechanics and also reduce the force here by this kind of cantilever here. Okay, any question on this? This is the first principle that we right. Any questions? There is no assumption of B1 is equal to B2 here, right? That's not an assumption. The assumption is the fluid is static, and by saying the fluid is static, that means the pressure at the horizontal plane will be the same, right? So it's kind of like a result of this assumption. Okay. There is more application into this that we gonna cover. That was my plan to finish all this today, but I'm fine with that as long as we try to understand carefully, what is variation of pressure and how can we apply forces on a fluid in simple example like this. So next time we'll talk about the manometry and maybe solve a few problems on that, and then start in forces over surfaces. Any questions? I'll stop here. Okay. You guys have a good day, and we'll see you Thursday.
Professor, can I ask a question?
Sure, yeah. I have an office hour after this. You can start asking. I have no problem. I'll be here.
Okay. Do you mind explaining what would happen if we change the fluid in the last example?
I will tell you, for example, if I put different oil, do you think it would be any difference? The force?
But we didn't use
exactly
a specific weight for it. So I'm thinking we could just change water to it.
Any fluid, right? The other consideration for using oil versus water, other factor related to corrosion, for example. You are not going to see, for example, a hydraulic device that has a water instead of an oil because of the corrosion and rust and other things, right? Evaporation of this oil, if you leave, if there are some leakage of this water, of course it's going to be empty after some time because evaporation of this water will be easier. So hydraulics, using oil versus water in hydraulic machines is not based on force transmission. It's based on completely other things. But any liquid will do the same. Make sense?
Yes, and then now I see that you changed the positions of the pressure, where we're assuming P1, P2.
Yeah.
But then in that picture you said they're about the same.
They are not about the same.
On the next example, I just saw that.
No, yeah, but this is something else we're gonna talk about.
Okay.
Next time. This is measuring pressure in pipes and stuff like this. That's a different example.
Thank you.
Well, let me stop recording this. So.